Hi, my name is Alex Barajas. I'm a PhD student at Oregon State University, and today I'll be going over marine power dynamics. Marine power dynamics is a open source Julia-based dynamic grid solver. Um, this package was developed with the intention to integrate wave energy converters onto dynamic grid simulations. Um, this is a fork from Power Dynamics. We can see the commit that we forked from here. Um, the reason for the fork was we wanted to include time series integration directly into the solver, which wasn't offered by the base. Uh, in this slide here, I'm going to kind of go over kind of how how the software works a bit. Um, but at a high level, essentially, we'll be having a Wexam run uh, of any modeler, such as sorry, not modeler, as any model such as RM3. We're outputting our time series data, our relative displacement, our K, our C parameters from Wexam and loading them into a CSV or a JSON file. And from there, we're pointing that CSV or JSON file directly into our linear PTO node, um, which lives in Marine Power Dynamics. That might make more sense when we look at an example here. Um, so here's an example that we have for the software. We're looking at IEEE 14. Um, and in this example that's available on GitHub, we'll be going through doing a stability test, looking at a line outage with looking at the baseline IEEE 14 and then an IEEE 14 case with a WEC on there. So here, this is just basic loading in packages, uh, creating some directories that you see here on the left. So one of the first things we do in this package is we build our grids. Um, so this IEEE 14 bus case is based from this source here. So here we can see that we're building our 14 buses. We have our branches, um, and then I built this single line diagram of a plotter so we can see what our grid looks like at a glance. Same thing here. We're creating a bus 15 case here, and the only difference is here is our linear PTO model. Um, and here we're passing some parameters. And something I'd like to bring your attention to is this JSON file that we're passing over. Um, this is the JSON file that's produced by Wexam. Um, and here on the left-hand side in this file tree, we can see where that Wexam JSON file lives. And it has just our time series data that's derived from our user-defined function here. Again, all of this is available on GitHub if you want to get into it. Um, but so the Wexam run is pre-run of our RM3, and then we're just pointing our JSON file to our linear PTO node within the grid. And here we can see the SLD diagram as well. And here we can see that we have our bus right here, for a wave energy converter. Um, and the red one is our Slack, and then we can kind of hover over different components to see what they're about. Here, I wanted to show what the data looked like from Wexam. So here we can see the power out in watts, and then the wave elevation on the right um, of the from directly from the JSON. Cool. So here's the dynamic simulation portion of this example. First, we're running a flat run. A flat run means we're just running a dynamic simulation, but with no disturbances, nothing on there. Um, it's called a flat run a lot of times. Uh, so output looks good, everything looks great, and we're running that flat run for both IEEE 14 and 15, just trying to get a baseline, mainly to compare to IEEE 14, and also compare to the when we run our fault. Here's our fault scenario. We're actually just doing a line outage. Um, Here we're taking out the line between bus 2 and bus 5. You can scroll up to here and kind of see which line that would be, bus 2 and bus 5. So we're cutting this line out quite a bit far from the wet grid, or sorry, from the wave energy converter branch. Oh, sorry about that. So yeah, so we're cutting out that line um, and seeing how everything responds, and that's being cut out at 105 to 110. Um, Something I didn't mention before is we do a warm-up period for about 100 seconds to get the system to settle. Great, everything looks good. Here is the results part from this example. So this is looking at IEEE 14 at the flat case to 160 seconds, 100 seconds to 160 seconds. Everything looks flat, everything looks great. This is exactly what we expected. Um, Here's the case with the WEC on there. Um, Everything looks great. You might notice in the top right that our frequency looks a bit crazy. But if you look at the units, the frequency is doing okay. We're just having that irregular injection of power. Here's looking at the line outage at IEEE 14. Again, this is what we're comparing against. Everything looks great. We're seeing our line outage at 105 and coming back at 110. And here is a case with um, the WEC on there. We're seeing relatively similar behavior as well. Another feature we have here is just saving out the functions or saving out the data to be looked at later. And then here's some of the data that we saved out um, for analysis. Here is the analysis portion of the example. Lots of boilerplate code, um, but we can see max derivation, negative peak, RMS, things like that. I believe there's another plotting function here somewhere. Uh, But yeah, so in conclusion, we're using this linear PTO node on our grid as our proxy. So we were successfully able to take our hydrodynamic model, hydrodynamic simulation from WexSim and integrate it on this open source dynamic grid modeler. Thank you so much for watching. The example is available on GitHub. If you have any questions, feel free to email me or raise a comment in on the GitHub issues. Thank you.